Welcome to the Calc AB Notes on Accumulation. The idea of accumulation is the idea of adding and collecting areas. Typically, we're going to use this with integrals, but it's the idea of adding new amounts to old amounts. And that would tell you a final amount. For example, if we're talking about snow, and I told you that maybe in January we had 13 inches of snow, that's not totally crazy because that's kind of what happened in Reno this year. And then maybe in February we had 2 inches of snow. In March we had 1 inch of snow. We could say that we had an accumulation of 16 inches in that time frame. So it's that idea. However, how would integrals somehow relate to this? Well, integrals will come into play with this if maybe we have information about a rate and we want to undo that rate to find an amount. Here's the accumulation formula. F of B for some amount at time or input value B could be found by doing F of A, which is some other amount at a different input, plus the definite integral from A to B of f prime of x dx, or f prime of t dt, whatever variable we're using. Something to notice, the input of the known amount that you're starting with needs to be the lower limit of your integral. The input of the ending amount that you would like to find needs to be the ending limit, the top limit for your definite integral. Also, something to keep in mind is that f and b are amounts of function f of b and f of a, versus f prime is the rate of f, and you're going to undo that rate to make this now another amount that you're adding on, and that's going to help us land at b. Now, where does this come from? This actually comes from the first fundamental theorem of calculus. The first fundamental theorem of calculus is what we use actually when we're evaluating a definite integral. If I'm taking the integral from a to b of f prime of x dx, well, the integral would undo the derivative. The antiderivative and the derivative are inverse operations. They would undo each other, leaving me with f of x, which would need to be evaluated at b and a. So another way to think of this is that the definite integral from a to b of f prime of x dx is equal to f of b minus f of a when I do my evaluation. Well, if I want to isolate f of b, I could do that by adding f of a to both sides. And I would end up with, I'm just going to flip-flop my left and right-hand sides, f of b is equal to f of a plus the definite integral from a to b of f prime of x dx. You might wonder why I've got f of a in the front and on the back. You could write in either spot, but what ends up happening is students get lazy with their differentials. And if you don't write your differential and you write like plus f of a after that, people might be confused. They might think that you're trying to integrate the f of a when you're not. So when might you use this? Here's an example. Let's say you know some rate. This is totally made up equation, by the way. Let's say the rate of rain falling per month during 2012 in a specific region can be modeled by this function. Keep in mind, r of t is some rate. This is like f prime. R is the inches of rainfall per month. There's just kind of more validation that this is a rate. T is the number of months after March. So the way we're measuring our input is the number of months after March. By the end of March in 2012, this region has accumulated 2 inches of rainfall. Well, this is an ordered pair. By the end of March 2012, we have 2 inches. So let's say I let A of t be the amount of rainfall for any specific month, or for the accumulation amount so far. Well, if by the end of March, and we're measuring t as months after March, this information, A of 0, is 2. If we're looking at months after March, we're starting with 2 inches after March. So if we want to find the total rainfall by the amount of July, well, July is the 7th month, March is the 3rd month, 7 minus 3 is 4. We're trying to find the 4th A after the 4th month, after 4 months have gone after March. Well, we can use the accumulation formula if we recognize so sorry. If we recognize that this A of 4 is like F of B, it's the same idea. It's our ending amount. Well, we would need to have some other known amount, which they gave me A of 0, plus the definite integral. Now my limits, 0 must be the bottom limit and 4 must be the top limit. These must match. Wherever I am starting off needs to be the starting amount for my integral, and wherever I would like to end needs to be the ending limit for my integral. And then I want to undo a rate in order to find an additional amount to get my total amount. And again, we knew that A of 0 is 2. So if I wanted to find this total, I can use my calculator. I already defined this function of R, and I could do 2 plus, I'll use shift plus here, the definite integral from 0 to 4, since I want to go to 4 months after March, of R of t dt. I'm going to round this to 3 decimal places or more, and I'll get 14.267 inches. Let's take a look at the next one. I now want to do the total amount of rainfall by the end of November. So I want to find the total amount by the end of November. The most common mistake is people put 11 here, but that's wrong. Keep in mind, we're measuring the months after March. November is the 11th month, March is the 3rd month, so we want to find A of 8. From here, I can again use A of 0. I could also use A of 4 if I wanted, but A of 4 has some decimals that maybe I'm worried about rounding properly, so I'm going to use A of 0 to 8 of R of t dt. This is the only work you need to show. This is your setup, just the accumulation formula. From here, I'll use the calculator. Now, one nice thing about the calculator is you can use the calculator and retype it. If you go back and you arrow up and you highlight this and hit enter, it's going to recopy it as a live entry, and I'm just going to change the upper limit to 8. And totally unrealistic answer. I don't know where this is, a rainforest or what. We got like feet, like multiple feet of rain that year, but 93.733 inches. And now I want to look for the entire year. So the entire year would end at the month of December. Again, we're measuring after March, so we want to find A of 9. Again, I'll start at A of 0, but I do have a couple other options. Now that I know A of 4, and now that I know A of 8, I could have done this differently and started with one of those numbers instead. But I'll do A of 0 because it's easy to type. And then I'll go, my definite integral would need to go from 0 to 9 of R of t dt. Keep in mind, this needs to be a rate here that we're undoing. I'm going to use that same kind of method before with the calculator of highlighting it, hitting enter so that it copies, and then I'll just change whatever I want to change, which in this case, I just want to change the upper limit to 9, and I get totally crazy number, 131.6 inches. So there's our first example of how to use the accumulation formula. Let's take a look at another one. On a certain day, the changes in temperature in a greenhouse beginning at noon are represented by F of t. There's the formula for F of t. T is the number of hours after noon. If at noon the temperature is 95, find the temperature at 5 p.m. I'm going to again let A of t be whatever I guess I want it to be the temperature at any time. And they told me the temperature at noon, which would be 0 hours after noon, is 95. This is my starting temperature. I want to find the temperature at 5 p.m., which is 5 hours later. So A of 5 could be found by doing A of 0 plus the definite integral from 0 to 5 of F of t dt. And so since I'm only going to use F of t once, I won't bother defining it. I'll just type it into the calculator. For A of 0, I'll use 95.
How much longer is it going to be?
That's all right. So I'm going to go ahead and enter this in. Let's see, F of t. I'm trying to memorize this, sine of t over 2. We'll see how this goes. So I have 95 as my initial amount, plus shift plus. I'm going from 0 to 5 hours. And I've already forgotten. I guess sine of t over 2 is F. dt. And I end up with some answer that is not a decimal. So just as a reminder, above the enter sign, you have the approximate symbol. And I'm just going to change that real quickly to 98.602 degrees Fahrenheit, I believe. And yeah, it says Fahrenheit. Units are required, by the way. All of these are word problems. They have units on here. We are finding amounts, not rates. So please notice I never have like inches per, just inches. All right, number 3, this is a graph of f prime. And I want to find a value of f1. Well, if you just look at the graph, hopefully it makes sense that if you're trying to find stuff about f and you're given f prime, that you would need to integrate. And remember, when we integrate something, we're using the area model. And we're accumulating area from left to right. So what we know is that the amount of area accumulated up when x is 8 is a total of 4. Now that's kind of interesting if you take a look at this a little bit, because if I look at the area I already have, this area here is positive 2. This is 6, so from left to right I've accumulated 8. I've got a negative area here. So now I'm at an area accumulation total of 5. And if I keep going, I now add on 7 more, and I've got an area of 12. But they told me that at 8, I'm only supposed to have an accumulation of 4. What? Well, what we're not thinking about is that there's area over here. Probably more like down here, I'm thinking I gotta have some negative area in some of this, maybe even some of each, that we are not seeing in the graph. But yet they've given us enough information to be able to figure this out. I'm gonna use the accumulation formula to do this. I want to find f of 1. I already know what f of 8 is. So if I add on to that the definite integral from 8 to 1 of f prime of x dx. Notice my limits are upside down, but they are in the correct order for the accumulation formula. So the way I can go ahead and evaluate this, f of 8, I'm told is 4. I'm going to reverse my integral here to a negative so that I have the proper limit order here. And so this would be 4 minus, and from 1 to 8, I'll start when x is 1, I have an area of 6. An area of negative 3, and an area of 7. So this is 4 minus 10. And I know that at negative 1, with whatever area was already here, I'd have to accumulate negative 6 units. Units squared. There's no real units here in area. You can see there's nothing in the problem that way. All right, last one. A water tank holds 1,200 gallons of water at time t. I'm going to use A again to represent the amount. And so the amount of gallons, or the number of gallons, the amount of water. And so at time 0, I have 1,200 gallons of water. Water is pumped into the tank at a constant rate of this. Now be careful here, what's being squared is the argument. If they wanted to square sine, it would look something like this. If they wanted to square even the 95 root t and the sine, it would look like that. So what's implied is that the argument is being squared here. We're gonna call this a rate coming in. Water is also being removed from the tank at a different rate, right here. This is the rate that water is going out. So this one's the rate in, and R is the rate out. Again, what's being squared here is the argument. To the nearest gallon, how many gallons of water are in the tank after 18 hours? And so we're starting at time 0. So I want to find the amount at time 18. I can do that by starting with the amount at time 0 and adding on to this the definite integral from 0 to 18 of what? Well, we've got 2 rates here. They're both applying. We have some coming in. That would be a positive. And we have some being removed. That would be a negative. So rate in minus rate out dt. And now I'm going to enter this into the calculator. A sub 0, again, is 1,200. I'm going to have to do some toggling back and forth because I don't have these in front of me. Plus the definite integral from 0 to 18. And then I need, this is hard to type, by the way, so you might kind of want to watch this. W of t is 95 root t sine of t over 6 quantity squared. So 95 root t times the sine. Oh, I did, you could see I already have a typo. Let's fix that. So shift plus, sorry, it got a little crazy there with the deletes. All right, trying again. I got 95 times the square root of t. There we go. That's looking better. And then when you multiply a variable times a trig function, you should use the times button. So times the sine of, now t over 6 is going to be squared. Enter in another parenthesis right here. And then t over 6. Just scooch out of that for inner parentheses so that you're in between and square it like that. Let me just double check, make sure that that is a match. That's looking good. All right, and then I also have in this same integral, you could separate it. I'll show you that in a second. I need to subtract off the rate out, which is 275 sine of t over 3 quantity squared. So 275 sine, you could put a times there, but you don't have to with a constant multiplier, of t over 3 quantity squared. Notice the argument squared, and I put in another set of parentheses here. And then my differential is dt. And I get 1,825.066. What was it? 25. Now this said in the problem, to the nearest gallon. And when it says to the nearest gallon, it really does mean to the nearest gallon. It means to the nearest whole gallon. We are expected then to not have those decimals because we were told differently. And then this would be the unit of measurement is here. And these are the end of the notes for accumulation.